Most steels do not have a composition exactly at the 0.8% carbon. Low carbon steels normally have a composition between 0.8 and down to 0% carbon. And those steels will not, of course, have only a pyritic structure. They will also have some ferrite in the structure. During the cooling down from the austenite area down to the temperature where the tectoid structure, that is where the pearlite is formed, there is a precipitation of ferrite. And we will now look into that type of precipitation and how it looks when we form a structure in that type of steel. Here we see the phase diagram of the iron-carbon system at low carbon contents. Here we have the ectoid point at 0.8% carbon. And now we're going to focus on this interval here, from 0 up to 0.8% carbon. And especially an alloy with this sort composition, CO. And we start up here in the austenite area. It means that we have one phase. We have the one-phase austenite with grain boundaries. And then we start lowering the temperature. And when we come down here to this line, we start to precipitate ferrite as we come into the two-phase region, ferrite and austenite. And the ferrite will precipitate preferably in the grain boundaries, as that the crystallographic structure is disturbed, and we will save some energy if we precipitate the secondary phase here in these areas. And when the temperature goes down, the phases along the grain boundaries are going to grow and be thicker and thicker. And if you compare to the picture to the right, which is a real micrograph of a structure of this type of alloy, we will see that in these white areas are now the ferrite phase, and we can see rather clearly that it's lying in the grain boundaries, the original austenite grain boundaries, round like this, as we see in this picture. But as long as we are above this temperature, which is actually 727 degrees, the tectoid temperature, we will have austenite inside the grains. Only the ferrite has precipitated. But when we pass this line, the pearlite will form. So that at this position, the composition in the austenite, the carbon composition has moved down here. So when we pass this temperature, all the remaining austenite will turn into pearlite. As we see here, here we see pearlite regions. It's a large grain here and a large pearlite area. And we can also see what the pearlite consists of ferrite and cementite, which we have the composition far away here. And we can see maybe the thin cementite lines here, the plates of cementite are very thin compared to the ferrite, as we are positioned here rather closely to the ferrite actually in this two-phase region. So we end up here with a structure with pearlite, prootectoid, ferrite in the original austenite grain boundaries. We will look a little bit more now into the structure in a microscope. Here we see the microstructure as we saw it before, but now we're going to focus on the whole structure. And the white phase is the ferrite, and the brown-grayish areas are the pearlite, as we learned before. Here we see a higher magnification, and now we're going to close up on one point here that we recognized from before. And we can also see here first a pearlite area, original austenite grain, and here the white phases are the ferrite. We see how it has lined up in the original austenite grain boundaries. There are larger grains, there are smaller grains, and here is a large grain as we looked at before when we looked at the pearlite. So here we see the whole structure. Now we're going to use the knowledge about the lever rule and couple the carbon content to the structure. Now we will use the phase diagram to calculate the fraction pearlite in an alloy with a certain composition. So the question is fraction perlite at composition CO. And CO is here on this line. And if you look here, we see that this distance is rather short. We are rather close to the ferrite. It means that we have dominating ferrite. The fraction perlite, it will be this distance in relation to the total distance here. So we can have that by taking CO minus n, which is this point, and divided by the whole distance, which is, we call that O here, minus n. And now we should figure out what are these letters. CO is here, and we have to judge where we are here, and we see that it's about 0.25% carbon. And the N, we know that's the maximum solubility, and that's 0.022. And O is of course 0.8, that's the perlite composition. So now we can just add this into the equation here, 0.25 minus 0.022 divided by 0.8 minus 0.022. So this is a fraction, and if you calculate this we get 0.29. Which means that roughly 30% of the structure is perlite. And we can go back to the figure a little bit here and see that the distance here are shorter, and we are relatively close to the ferrite. It means that we will have more ferrite, and we have now calculated that we have 70% ferrite and 30% perlite with this composition. Now we will do this in a different way. We will start looking at the microstructure, and then we will try to figure out what is the composition of the alloy. We will use the microstructure here to the right. And first we have to identify what do we see in the microstructure. Well, we know now that these brownish areas are perlite, and the white or light areas around here in the grain boundaries are ferrite. So what we should do is try to evaluate how much ferrite and how much perlite do we have in this structure. Of course, we should need to look in a large part of the sample, look in the microscope and look at as large part as possible. And then there are different techniques. One can use image analysis directly from the microscope, which is the best, but one can also do more simpler techniques by putting lines and measure how large portion of the line is in the respective phase. If we do so in this case, we will end up with a result that shows that we have 75% perlite and 25% ferrite. With that data, we will go into the phase diagram. So now we're going to focus on this part. We know that we have more perlite than ferrite, so a first rough adjustment will be that we must be in this part of the phase diagram. But let's do this now numerically. Now we go to the phase diagram, and we come with the knowledge that we have about 75% perlite. And then we can make the assumption that we will be in this region, and we put a line somewhere we assume that we will end up with a result. We will call this X%, and then we start using the lever rule. We should also write down here what we know. We know that the fraction perlite 70%, 75%, or the fraction is 0.75. But if you use the lever rule here now, we know that this distance relative to the whole distance here will give us the fraction perlite. So we have to sign what is this? Well, it's the distance there is x minus n, this distance, and the whole distance is again O minus n. And this we now know is 0.75 refraction per light. So now we just resolve this and have to put in numerical values, and the x we don't know. O is again 0.8 and n is again 0.022. So if we put in these data in the equation, we will solve x, and then we will find that x is 0.60% carbon. So based from the microstructure we have now calculated that we have about 0.6% carbon in this steel. And if you look a little bit closer into this, we can also do this easier. When you get some practice, it's easy to do this. Realize that n is rather close to 0. It means that if we are at 75% per light, we are on the fourth of this distance from 0.8 to 0, which means it's 0.2 from 0.8, which means that we come up at 0.6. So after some practice, it's possible to directly see on the structure and directly judge the fraction of perlite and ferrite, and easily in the head calculate about what carbon content we have. And this is a very practical thing to do.